I remember reading a technical forecast not too long ago that treated the silicon carbide market like a closed book. The narrative was firm. Wolfspeed, the American giant, had effectively won by scaling to 8-inch wafers, while Chinese suppliers were portrayed as perpetually stuck on the smaller, less efficient 6-inch technology. It was the classic story of a high-tech lead that seemed insurmountable, a gap that experts claimed would take at least a decade to bridge. But recently, I came across an update from a production line that felt like a glitch in that narrative. It wasn't a story of gradual catch-up, it was a total leapfrog. A company called EpiWorld had just produced the world's first 12-inch SiC epitaxial wafer using a full domestic supply chain. They didn't just reach the 8-inch finish line, they realized the finish line had moved and decided to sprint past it. What's truly striking is the sheer velocity of the shift. Only a year ago, in early 2023, these same suppliers were just beginning to find their footing with 8-inch production. By 2024, they hadn't just stabilized. They had quietly captured over 31% of the entire global market. Now, while the rest of the world is still debating the cost-effectiveness of 8-inch transitions, China's SuperSic and Jingshan have already moved to 12-inch trial production, eyeing mass delivery by next year. Watching this unfold is like seeing a runner in a marathon suddenly swap their shoes for a jetpack mid-race. The ironclad advantage held by Western leaders has evaporated, replaced by a domestic ecosystem that now dominates the world's largest EV and new energy markets. It leaves you with a lingering, slightly unsettling question. If the gap we were told was permanent could vanish this quickly, who is actually setting the pace for the future of power electronics?
That speed is the absolute headline here. It really, it demands a deep dive into the underlying physics and, the economics. What we are witnessing is not just an incremental improvement, it's a fundamental reshaping of the material science hierarchy in power electronics.
Right.
For you, the listener, the key is understanding why silicon carbide is such a high-stakes material. Mm-hmm. It's the material foundation for the future of power applications. So think high-speed rail, massive solar farms, and critically, the high-voltage inverters in every single high-performance electric vehicle on the road today.
So it's basically everywhere in this new energy transition.
It is. It enables systems to operate at significantly higher frequencies, withstand much higher voltages, and handle extreme temperatures far better than traditional, standard silicon. Because of this, the global technology race has always centered on one crucial metric: larger wafers.
And larger wafers just mean cheaper chips at the end of the day.
Larger wafers directly translate to lower chip costs, which is the necessary condition for mass adoption and ultimately performance dominance.
Okay, let's unpack this. The conventional wisdom for years was that the technical hurdles involved in increasing the wafer size, especially for SiC, which is, it's notoriously difficult to grow. That meant the advantage was firmly with the incumbents who mastered 8-inch first. But the story here isn't just about scaling to 12-inch. It's about doing it with 100% self-sufficiency. Let's focus on this idea of domestic technological sovereignty, because that feels like the real strategic weapon being unveiled here.
That's the critical distinction. It really is. Many major international players have R&D programs targeting 12-inch CC, but their supply chains often rely on a patchwork of specialized high-precision equipment sourced globally.
Right, from all over.
Particularly from countries with, long-established semiconductor tool manufacturing expertise. The core breakthrough here is the combination of size and absolute localization.
Okay, so tell us what that localization actually looks like on the ground. When we say 100% localized, what parts of the process were historically the biggest dependency, and how have they solved that?
Well, historically, the difficulty was securing the high-precision machinery needed for the final stages. Things like the crystal growth furnaces themselves, the precision diamond saws for wafer cutting.
The really specialized stuff.
Exactly.
Right?
The specialized polishing equipment that can create a near-perfect surface on such a hard material, and then the inspection tools that verify minimal defect density. These are highly guarded technological domains.
Sure.
The announcement from Zhejiang and Jingshan Mechanical and Electrical, or Jingshan EMI, it changes the game entirely. They announced the launch of the world's first fully localized 12-inch 6C production line commissioned at their subsidiary, SuperSic, on September 26, 2025.
Wow.
And this isn't just assembling foreign equipment in a local factory. This means that every single step, from the initial highly challenging crystal growth phase through wafer cutting, detailed polishing, and final inspection, it all runs exclusively on domestically developed and manufactured equipment.
That is immense.
Oh,
and it speaks to a deliberate long-term national strategy coming to fruition. It means they've solved the equipment manufacturing puzzle, which is, like you said, often harder than perfecting the material itself. It signals true technological autonomy in this foundational material segment.
It does.
You're talking about moving from relying on external, often strategically controlled suppliers for key machinery
to controlling the entire technology stack internally.
To controlling the entire stack.
Absolutely. And the localization isn't just a claim, it's validated by the output. Hanting Technology, which operates under the brand name EpiWorld, launched the world's first 12-inch SiC epitaxial wafer shortly after. This epitaxial wafer is the final chemically processed material layer grown onto the substrate, ready to be fabricated into actual chips, the final product the industry needs.
Okay.
By successfully producing this wafer with stringent quality standards, they confirmed the viability and the maturity of the entire domestic ecosystem supporting it.
And when you look at the corporate players involved, the vertical integration becomes even clearer. We're not talking about 3 separate companies trying to work together. This is a powerful internal synergy.
Exactly. The key components are feeding into one another. The epitaxy equipment itself, the machinery used to grow that critical layer, is coming from Kyushu Semiconductor, which is a subsidiary of Jingsheng EMI.
Okay, so it's all in-house.
All in-house. And the actual substrate, the foundational SiC wafer, is being supplied by Zhejiang Jingru, another entity under the SuperSic umbrella. This integrated vertical solution is incredibly powerful because it allows for rapid feedback and iteration.
I see.
If there's a defect in the substrate maker and the epitaxy provider can communicate instantaneously, adjust the equipment, and refine the process all without relying on external vendors or sharing proprietary data.
That vertical integration is a massive accelerant. And if we look at Hanting Technology's history, their market capture was already moving at, breakneck speed, even before this 12-inch breakthrough.
Their history really does set the stage for this leap. Hanting was the first company in Greater China to achieve and commercialize 8-inch technology. By 2024, they weren't just a participant. They became the only global company mass-selling 8-inch SiC epitaxial wafers, managing to capture over 31% of the entire global market share that year.
31%? In just a year or two.
Think about that time frame, going from fledgling 8-inch trials to commanding nearly a third of the global market in 2 years. That isn't just catching up. That is taking the lead and defining the commercial standards.
And the quality metrics they are claiming for this new domestically produced 12-inch wafers are critical, especially when we talk about high reliability automotive components. They aren't just pushing for size and sacrificing quality.
Absolutely not. They're hitting high reliability standards right out of the gate. For example, they report the epitaxial layer non-uniformity, so how consistent the critical growth layer is across that massive 12-inch surface is held to less than or equal to 3%.
And for listeners who may not deal with semiconductor physics every day, why is that non-uniformity number so important? What does that actually mean?
It matters hugely for the final manufacturing yield. If the epitaxial layer isn't uniform, if it's, say, too thick in one spot and too thin in another, it means the devices built on those spots will fail the performance test.
Right.
On a 12-inch wafer, maintaining 3% uniformity across 300 millimeters of incredibly complex material is a triumph of process control. It directly influences how many usable chips you can cut from that wafer.
And speaking of usable chips, they are reporting remarkable chip yields, even for these early stages of 12-inch production.
Yes, they're reporting chip yields of greater than 96% for standard 2mm by 2mm chips. That high yield, combined with the massive increase in usable area provided by the 12-inch wafer, is the perfect storm for economic advantage. This isn't just a technical paper win. This is the core of the business case we need to discuss next. The entire operation is structured for immediate, cost-effective volume production.
That's the perfect transition, because here's where the narrative shifts from an internal technological victory to an external market disruption. This high-tech lab achievement translates directly into a tangible consumer cost advantage. We're moving from the complexity of material science to the democratizing force of affordability.
You have to look at this through the lens of productivity and cost per chip. In high-volume manufacturing, the single largest lever you have for reducing cost is increasing the surface area you process simultaneously. The capital equipment costs, the furnace, the inspection tools, the fab time, they don't scale linearly with wafer size. The 12-inch wafer absorbs a lot of those fixed costs across many, many more chips.
So let's break down the sheer numbers of this productivity multiplier, because this is the core of the business case that will transform the global EV and renewable energy markets.
When you look at the previous standard, the 6-inch wafer, and compare it to the new 12-inch wafer, the difference is just staggering. A 12-inch wafer yields 4.4 times more chips than a 6-inch wafer.
4.4 times.
That's more than 4 times the output from roughly the same manufacturing cycle time.
4 times the output. That's an insane increase in manufacturing efficiency. It means the throughput of a single manufacturing facility specializing in 12-inch immediately outpaces multiple 6-inch facilities.
But the comparison that truly defines the global race is against the 8-inch standard, which was, until very recently, considered the ultimate objective for Western leaders.
Right.
Even compared to the 8-inch wafer, the 12-inch technology yields 2.3 times more chips. And some specific estimates from Jingsheng and SuperSic, factoring in their optimized process flow and high yields, place that efficiency boost even higher at 2.5 times more output per run.
So even stacked against the most advanced technology the rest of the world was struggling to ramp up, the 12-inch breakthrough offers more than double the chips per production run. Now, is the area ratio exactly double? I mean, a 12-inch is geometrically larger, but the key is the yield, the usable area. How do they maintain such a high yield when the material is so prone to defects, which usually become amplified on larger surfaces?
That's a sophisticated question. The yield challenge is precisely why this 12-inch milestone is such a major technical achievement. In theory, moving from 8-inch to 12-inch means the area increases by about 2.25 times.
Okay.
However, historically, as you scale up, the defect density increases, meaning the usable area increase is often less than the geometric gain.
Right, you get more waste at the edges.
Exactly. The fact that these suppliers are claiming a 2.3x to 2.5x chip yield increase suggests two things. First, that their defect control, which we can get into later, is world-class, allowing the maximum possible number of chips to be cut. And second, the chips they are targeting, the power devices for automotive use, might be optimized in size to make the best use of the 12-inch perimeter, maximizing the cutting efficiency.
That efficiency gain, that productivity multiplier, leads directly to the cost revolution. What does this mean for the price of the actual components that go into products like an EV?
This is the massive downstream effect. Industry analysts, having observed the technical maturity and aggressive volume production planning, estimate that volume production of 12-inch SiC could reduce the overall wafer cost, the cost of the raw process material, by up to 40% compared to the 6-inch wafers that defined the market just a few years ago.
40%. A 40% reduction in the core material cost is unheard of in a high-tech sector in such a short period. This isn't marginal trimming. This is a fundamental repricing of the technology.
It is absolutely transformative for downstream industries, especially for the global electric vehicle sector. SiC is a premium material. It's one of the most expensive components in a high-performance EV inverter.
Right.
If you slash the material cost by 40%, the impact on the final product is immediate. We're talking about critical components like automotive-grade power modules, which rely heavily on these SiC chips. These modules could potentially drop in cost from about $150 down to around $90 once 12-inch production hits commercial scale.
Wait, I have to stop you there. A $60 drop per module is massive, especially when a single EV might use several modules. But we're talking about highly specialized, high reliability components destined for automotive environments. I mean, they have extremely stringent safety and endurance requirements. So how do we know these potentially cheaper $90 power modules are hitting the same demanding automotive reliability standards as the incumbent higher price modules? Is there a risk of a quality trade-off for that rapid cost reduction?
That's a valid critical concern, and it's where the high yield and defect control we just discussed come into play. The high reliability standards are non-negotiable for automotive use. The key insight is that the cost reduction isn't coming from using cheaper materials or relaxing quality control.
I see.
The reduction comes from utilizing the wafer surface much more effectively. If you have a 4.4x yield multiplier, you can afford to cut the price per chip dramatically while still maintaining or even increasing your profit margins.
So it's pure economies of scale.
Exactly. Furthermore, the early reported quality metrics, like the 96% chip yield and the excellent non-uniformity data, suggest they are starting with a material of very high inherent quality. This means the components coming off the 12-inch line are designed for high yield and high reliability from the outset, allowing the price to drop due to scale, not due to corner cutting.
That makes the shift even more strategically compelling. It transforms what was once a niche, expensive, high-performance technology into a high-volume, globally accessible commodity. And that speed is translating directly into revised market share projections.
The market shift is breathtakingly fast. Data from analysts like TrendForce project that China's SiC market share is set to jump dramatically. They anticipate a move from 35% in 2024 to a commanding 60% by 2025.
60%.
60%. That indicates a rapid, almost complete capture of global production volume, driven entirely by the cost and volume advantages inherent in this 12-inch capacity and localization.
And the domestic localization effort is stabilizing that advantage internally, making the supply chain highly resilient. We highlighted the 100% localization of the new 12-inch line, but overall, the localization of production equipment across the broader CZ industry has surpassed 80% domestically.
That equipment self-sufficiency is the ultimate defensive measure. It means the industry creates a self-reinforcing, powerful feedback loop. They invest in R&D for new equipment, they use that equipment to refine processes, and that refinement accelerates their development further, making them less susceptible to geopolitical or trade disruptions that might slow down their international competitors.
Right.
Companies like SuperSic, SiC, and Jingsheng are not stopping at the 12-inch breakthrough. They are already in the trial production phase and are aggressively eyeing mass delivery by next year. This trajectory from trial to mass market delivery within 12 to 18 months reinforces the confidence and speed of this entire strategic shift.
This 12-inch leap is so dramatic, it's easy to overlook the critical infrastructure that made it possible. They couldn't have jumped that far, that fast, without a massive simultaneous investment in the previous generation of technology. Before the 12-inch Leapfrog, Chinese suppliers aggressively scaled their 8-inch production, forming a robust, tiered industrial structure that provided the necessary capacity, technical know-how, and, crucially, the talent pool for this rapid advancement.
That foundation is arguably the most important strategic element. The 12-inch success is built on the mastery achieved at the 8-inch level. They didn't just scale, they built a highly structured, tiered industrial base designed for maximum output and continuous innovation. We can analyze this structure in three distinct layers based on their capacity goals and strategic function.
Okay, let's start with the heavy hitters, the Tier 1 players. These are the giants achieving serious scale and validating their product with global clients. What defines them?
Tier 1 is defined by a commitment to mass production, meaning capacity targets exceeding 100,000 wafers per year. This tier is spearheaded by SiC, TenkaBlue, and Sinan Optoelectronics. These companies have, astronomical expansion plans that speak volumes about their confidence in capturing global demand.
Give us a sense of that scale. What does 100,000 wafers per year mean in the context of the global market?
It means becoming a primary global supplier overnight. SiC, for example, aims to expand its 8-inch capacity to a massive 600,000 wafers annually by 2025.
Wow.
To put that into perspective, 600,000 8-inch wafers alone represents a substantial percentage of the world's current output capacity, forcing international incumbents to reassess their own volume plans.
And SiC isn't alone in that ambition.
Not at all. TenkaBlue has similarly aggressive targets, aiming for capacity between 500,000 and 800,000 wafers per year. And then you have Sinan Optoelectronics, which is strategically aligning itself by establishing a joint venture with a major international player, STMicroelectronics, in Chongqing, targeting 48,000 wafers per year initially.
That's a huge validation.
It is. That joint venture is a critical validation point, showing that their 8-inch product quality is sufficient to meet the supply chain standards of leading multinational device manufacturers.
So Tier 1 is all about sheer competitive volume.
Yeah.
Where does Tier 2 fit into this ecosystem?
Tier 2 is the rapid scale-up and geographical expansion arm. These players are currently operating at a smaller, small to medium scale, perhaps 5,000 to 10,000 wafers per year. This includes crucial subsidiaries like Nansand and independent companies like JSG.
Okay.
The strategic importance of Tier 2 is the velocity of their ambition. Nansand, for instance, is aggressively scaling, aiming for a massive expansion to 500,000 wafers per year by 2025, essentially mirroring the volume goals of the Tier 1 leaders, but perhaps focusing on slightly different niches or geographies.
And I noticed JSG is already making international moves.
That's right. JSG is already expanding internationally, establishing a facility in Malaysia. This demonstrates their preparedness to serve the broader regional and global supply chain, showing that this capacity buildup is not just inward-focused, but is designed to provide stable, high-volume supply across Asia.
Which strengthens the regional industrial landscape for partners, say, in Southeast Asia.
Exactly.
And finally, Tier 3. the pilot and sampling stage. Why is it important to maintain a pipeline of smaller players in a field dominated by such massive scale?
Tier 3, featuring firms like Kiyu Semiconductor and Tiansheng Semiconductor, with capacities below 5,000 wafers per year, acts as the crucial R&D pipeline. They are the innovation engine.
So they're more agile.
Right. While Tier 1 focuses on optimized mass production, Tier 3 can afford to take higher risks on new processing methods, experimental materials, or defect reduction techniques. This tiered structure ensures a dynamic environment where the major players push volume, the mid-tier rapidly scales that volume, and the smaller players focus on continuous technological breakthroughs that can eventually feed into the established production lines.
But capacity means nothing without quality. Let's talk about the specific technological sophistication they achieved at the 8-inch stage that laid the necessary groundwork for the 12-inch leap. What material science breakthroughs were necessary?
The advancements in crystal growth and defect control are truly what enabled the 12-inch jump. The traditional method for growing SiC crystals is called physical vapor transport, or PVT. However, SiC pioneered the use of liquid phase methods for crystal growth.
For listeners who haven't spent time in a materials lab, how does that liquid phase method physically differ from PVT, and why is it superior for manufacturing large, high-quality wafers?
It's a significant technical shift. The standard PVT method involves vaporizing the SiC source material and allowing it to deposit onto a seed crystal in a high-temperature furnace. It's effective, but it's difficult to control the sheer size and uniformity of the resulting crystal, and it's prone to creating internal structural defects.
Okay.
Liquid phase methods involve dissolving the SiC source in a metallic solvent and growing the crystal from that liquid solution. Think of it like growing a salt crystal from water, but at 2,000 degrees Celsius and under immense pressure.
Right.
The liquid phase allows for a much slower, more controlled growth environment, which helps in flushing out impurities and reducing the internal stress that causes defects. This allowed SiC to produce macro defect-free 8-inch substrates, achieving crystal thicknesses over 60 millimeters. That thickness is crucial for stability during all the subsequent high-stress cutting and polishing steps, and it far exceeds the typical industry average for 8-inch wafers grown by older methods.
So it's not just the width that they mastered, it's the structural integrity and thickness of the material, making it robust enough to handle the 12-inch jump.
Precisely. And that mastery translated directly into performance. Tanka Blue, for instance, developed low-resistivity 8-inch substrates, achieving levels between 7 and 12 milliamps per centimeter squared. This is a technical triumph because low resistivity is absolutely vital for power devices.
And I imagine low resistance is key to efficiency in an electric vehicle, right?
It's the difference between range anxiety and a successful journey. In power electronics, minimizing resistance is maximizing efficiency. By achieving these low resistivity substrates, they are reducing the overall power device resistance by 2% to 4%. Every percentage point saved in efficiency translates into massive energy savings in grid infrastructure, or extended battery life and faster charging times in an EV.
And the final hurdle, the most notorious one in SiC manufacturing, is defect control. SiC is an incredibly hard, brittle crystal, making it notoriously difficult to grow without internal flaws.
This is the true measure of maturity. Those internal flaws are called dislocations, and they are responsible for device failure. 2 types are critical: threading screw dislocation, or TSD, and basal plane dislocation, BPD.
Okay.
TSDs run vertically through the wafer and can cause immediate catastrophic device failure under voltage. BPDs run horizontally and can degrade performance over time.
It sounds impossible to grow a crystal the size of a dinner plate without any major cracks or structural weaknesses inside, especially when you consider the high temperatures and pressures involved.
It is intensely difficult, but they succeeded. Nansand and Jinyu Semiconductor achieved industry-leading defect densities, proving the high material quality. SiC pushed this mastery even further in their 8-inch substrates, achieving near-zero TSD and extremely low BPD densities. Achieving near-zero TSD is monumental because it means their crystal growth process is fundamentally stable, guaranteeing that their chips will withstand the high voltages required by automotive and energy applications without burning out.
The mastery of 8-inch technology was clearly the training ground. They proved the capacity, the quality, and the stability. Now they've leveraged that expertise to hit 12-inch localization. Let's look at the strategic ramifications, how this cost reduction and localization translates into major strategic advantages globally, extending the reach of this technology far beyond their domestic borders.
This is where we talk about global industry stability. The breakthrough isn't just about internal self-sufficiency. It's about providing a reliable, cost-effective industrial anchor for the entire surrounding ecosystem, especially in high-growth regions.
And if we look at the dominant driver for CEA today, it remains the automotive and energy sectors.
Undeniably, SiC's superior performance and high voltage resistance and excellent heat tolerance makes it mandatory for EV power modules, the inverters that control the battery power flow, and the fast chargers that replenish that energy. The market data is unambiguous. In 2024 alone, new energy vehicles, or NEVs, accounted for a staggering 73.1% of global SiC device consumption. It is the engine driving this expansion.
And the domestic localization effort is designed to feed that engine perfectly.
It is. Leading domestic suppliers like SiC, TankaBlue, and Sanan have secured major long-term orders for these EV power modules. As the world's largest automotive market transitions rapidly to electric vehicles, these companies are perfectly positioned to capture that domestic demand and increasingly international demand with their cost-effective 12-inch components. Beyond EVs, the renewable energy sector, solar inverters, wind power systems, and general industrial applications are also aggressively adopting these larger 8-inch substrates to gain higher efficiency across their infrastructure.
But the next frontier, and the most exciting potential market, goes far beyond cars and solar panels. The exponential demand for computational power driven by the AI boom is opening up a completely new, high-value application domain for SiC that very few predicted even 2 years ago.
That's where the technology is heading next. AI data centers, which are powered by enormous GPU clusters, are becoming fundamentally bottlenecked by two interconnected factors: the sheer power demand and the resulting thermal management nightmare. These centers require extreme amounts of energy, and conventional silicon solutions struggle desperately under the sustained high thermal load necessary for training complex AI models.
So we're seeing a scenario where SiC moves from being a specialized material for vehicle powertrains to a critical enabler of the AI infrastructure itself.
Exactly. If you want to increase the power density in a rack of servers, that is, pack more computational power into a smaller space, you need to manage the heat. With its superior thermal conductivity and inherent high temperature endurance, SiC power modules can significantly improve the server power efficiency, reducing the massive energy loss that occurs during high-load computation.
So you get denser racks, more compute per square foot.
Denser, more powerful computing clusters without the systems failing due to overheating or incurring exponentially higher operational energy waste.
Now, here is the most intriguing development that shifts SiC from a peripheral power component into a core chip technology. The rumored experiment by NVIDIA. There are reports that NVIDIA may plan to replace traditional silicon interposers with SiC in its upcoming Rubin GPU architecture.
If this rumor proves true, it is an absolute game changer. This moves Sensity out of the realm of power conditioning and straight into core AI chip packaging.
Okay, so for listeners, what's an interposer?
An interposer is essentially the passive foundation on which the main, highly complex processor chip, the GPU, and its high-speed memory modules are mounted. It acts as a bridge, managing all the high-speed electrical communication between them. Traditionally, this is made of silicon.
But replacing silicon with SiC in that foundational layer sounds revolutionary. What specific non-power-related benefits does Sensei provide inside the core chip packaging that traditional silicon can't offer?
The benefits are critical for the next generation of AI chips, which require unprecedented thermal and electrical performance. First, better heat dissipation. Sensei moves heat away from the sensitive GPU and memory components far more effectively than silicon. This is vital because modern GPUs generate enormous heat, and managing it determines whether the chip can run at full speed or has to throttle down.
So you get more performance for longer.
Right. Using CRC allows for denser GPU clusters to operate without immediate thermal limitations. Second, lower electrical resistance. Lower resistance means that the data transmission paths between the chips and the memory are faster and more efficient. In AI training, where billions of data points move continuously, every millisecond saved in latency is a massive gain in computational throughput. And third, higher thermal thresholds. This allows those incredibly expensive GPUs to operate longer and harder at peak performance, maximizing the return on investment.
It's a whole new market.
This single application, if adopted by a major player like NVIDIA, could fundamentally open a completely new, high-value market domain for large-diameter SiC wafers, further accelerating the need for high-volume 12-inch capacity.
That is a massive potential driver for the conductive sealer market. But the localization push isn't limiting itself to power or computation. They are simultaneously focusing on non-conductive or optical-grade CLRC. That's a niche, highly precise material segment, correct?
It's the next big strategic move designed to target high-end components where quality and exotic material properties are paramount. The focus is expanding beyond the familiar conductive power devices into photonics and ultra-precision optics. Shenzhen Kutan Semiconductor, through its subsidiary, announced plans to build what is projected to be the world's largest 12-inch optical-grade SiC production base in Huizhou, Guangdong, backed by a major RMB 1.15 billion investment.
And this optical CC is targeting a completely different set of highly specialized applications. What are those drivers?
The drivers are next-generation consumer electronics and advanced communications infrastructure. This high-purity material is designed for optical waveguide materials, which are critical components for AR and VR lenses, the lenses that project augmented reality images onto the world.
Right.
It's also vital for high-speed optical communications, LiDAR systems used in advanced autonomous vehicles, and interestingly, for advanced 2.5D and 3D chip packaging methods used in the most complex AI chips.
And the technical specification of this optical material is what makes it so valuable and historically difficult to source.
It must be almost perfectly pure. This material is characterized by extremely low absorption, very high light transmittance, and crucially, an ultra-high refractive index of 2.7. This specific combination is incredibly desirable because it allows for the creation of ultra-thin, high-performance optical components, which is essential for slim, lightweight consumer electronics like the next generation of AR glasses.
And this project isn't just about creating a new product. It's directly targeted at addressing long-standing supply gaps.
Precisely. This entire project, which is aiming for an annual capacity of 200,000 wafers and a projected output value exceeding RMB 3.6 billion, is designed specifically to break the established foreign monopolies in this highly specialized niche material segment. By achieving localized mass production of both conductive and optical SIM, the domestic industry is positioning itself for full-spectrum technological sovereignty.
So if we pull back, we are seeing a full-court press. They are dominating the high-volume, cost-sensitive power device market with conductive 12-inch SiC, while simultaneously conquering the high-precision, low-volume niche market with optical SiC and exploring completely new high-value applications like the AI interposer.
It is a decisive, full-spectrum strategic push. The successful and localized 12-inch SiC breakthrough is more than a momentary technical win. It's a crucial and foundational step towards strengthening domestic innovation capacity and achieving comprehensive technological sovereignty across the entire SiC material spectrum. This effort positions the country not just to participate in, but to actively lead the global transformation toward electrification, new energy systems, and the fundamental infrastructure required for the age of artificial intelligence.
What a monumental shift. The gap that was deemed insurmountable just a year ago has vanished. We've watched the city's supply chain transition from a perceived follower status to setting the global pace for future power electronics, providing robust stability and dramatic cost advantages for industrial partners worldwide. The foundation laid by the aggressive scaling of 8-inch capacity, with Tier 1 players targeting hundreds of thousands of wafers annually, mastering complex techniques like liquid phase crystal growth and achieving critical near-zero defect densities, is what fueled the speed and confidence of the 12-inch leap.
The focus now shifts entirely from demonstrating capability to optimizing full-scale commercialization. With the massive cost advantage provided by the 12-inch wafers reducing power module cost by roughly 40% and increasing chip yields by 4.4 times over the old 6-inch standard, and with SUF moving into entirely new, high-value markets like AI chip packaging and high-end optical waveguides, the industry has achieved a level of resilience and self-reliance that guarantees its leading and stabilizing position in the future of global energy and computation. This shift represents the most rapid and decisive technological capture witnessed in the semiconductor materials market in decades.